Hello, good afternoon, everyone. Welcome to Grenoble, if you're not from here or not studying here. Welcome to the SoRAIM Winter School. My name is Xavi, and you might have received emails either from me or from Mathieu, if you're around. I am very happy to be here. It took a lot of work to organize this, but now this is past, and we have the opportunity to enjoy a bunch of talks. So I will give a short introduction to the school so that you have maybe the general context. And I guess that it will also be time for you to ask a few questions if you have some. There will be a demo after with this wonderful beast. That's how we call it in the lab. Demos are tricky. So be kind with Ari and be kind with us, because it might work, it might not work every day. It changes, right? So we have also recorded some videos so that you have proof that it actually worked at some point in time, in case it doesn't work today. All right. Okay, so the pointer doesn't work. So SoRAIM stands for Social Robotics, AI, and Multimedia. As you might have seen in the webpage, we are going to discuss things like speech processing, computer vision, of course, dialogue modeling, navigation, and all sorts of, let's say, skills that a robot would need to have some sort of social intelligence. All right. We have organized this in the context of the AIDS 2020 Spring Project, which is something that started in January 2020, which is more than 4 years ago, and it will end this month of May. And the idea was to present some of the things that we have achieved during these almost 4.5 years. Of course, we cannot present everything because it would take too long. And we have coupled this with some with a few invited speakers. I will explain this maybe later. So the overall objective of this project is to have these socially assistive robots, right? Being able to perform these multimodal and multi-party interactions with people. So by multi-party, it means that the robot could interact with 2 or more people, like in a group, right? Which is very different from, let's say, dyadic interactions when it's like face-to-face or one-to-one interaction, all right? So I'm not going to give lots of details of how the project is structured because it would take too long, and it's not really very important now, but for you to understand, because that's also how the program has been structured, is that we had like 3 main pillars. One which was on robot perception, right? Like how the robot senses the environment, right? Then the second pillar on robot action, like what does the robot do with that sensing, right? How does the robot act, right? And then of course the final pillar, which is, okay, it's all fine to develop all these models, but then do they actually work? How do we measure, right, that these things actually work? So that's the third pillar, which is the validation. And you have here a few pictures of the robot with actual patients in a daycare hospital in Paris. Okay, so this means that we have a platform that is standing there and discussing with real patients. Some of them may have dementia or other cognitive troubles, and the robot is currently on hold because the person that takes care of that is Lorian, that just arrived, and so she is our experimenter, and of course it's holidays for the robot this week, okay, because she's attending the school. So we are 8 different partners that are spread all over Europe, and we all have our specific, let's say, expertise. And the point of showing this slide is just for every one of you to understand that if you want to achieve like a real system working in a real environment, it's very difficult to do that with a single research group or with one single industrial partner. Okay, you have to put together many different fields of expertise to be able to do something like that, all right? So if you are in your lab trying to do something, just remember that maybe it will be better to reduce the scope of what you are trying to do and to prove a single point than targeting something that is super wide, for which you would need like a very large collaboration environment, or otherwise you try to build an European project or another kind of project to have such collaboration environment. So what are we going to have here in the school? We are going to have 8 plenary sessions. Each session consists of one, let's say, invited speaker external to the project that will give a talk on the recent progress on a topic, plus then a short presentation on 1 or 2 achievements related to the topic that have been, let's say, produced during the Spring project by one or many of the partners. And then we have a few, let's say, special sessions. One of them is a panel that's going to be tomorrow afternoon. We will have poster sessions, so some of you have submitted a poster, and then we will be very happy to come and discuss to you so that you can explain us what you are doing on your free time. We will also have some social activity on Thursday afternoon, and then a hands-on session on Friday. So I will now give some of the details of the program. I will start with the plenary sessions. So the first one is going to be given by Mark, which is in the University of Lincoln, paired with Séverin, which is HRI researcher at PAL Robotics. Okay. And basically the idea of this session is how to deploy these things. What do we need to do to deploy this kind of systems, right? So adaptation, software integration, deployment, all these ideas will be discussed there. And so every time, just in case I forget, there is this hands-on symbol, means that there will be one of the hands-on session will be related to that work package, to that topic, all right? The second plenary session is about experiments. So our invited speaker will be Vicky, which is right sitting here, coupled with Cyril. And Cyril is the CEO of a company that is actually selling robots. So they are very interested in that these things actually work, right? Because otherwise they cannot sell them. So going on, the third session is going to be about ethics, which is of course a crucial point in all this endeavor, especially because our experiments were in a daycare hospital, right? So the ethical part was even more important than if you would just run experiments in your lab. Not that it is not, but it's even more crucial. And then the fourth plenary session is about audiovisual perception. So Wenwu is traveling right now, and then Sharon, who is here, will be our spring speaker on how to use these 2 modalities for the robot to understand what's going on around. Then we move more towards, let's say, the action part with 2 plenary sessions, one on dialogue management by Gabriel, and then Daniel, that will be our spring speaker. And then the second one on, let's say, robot action, navigation, like moving around. So Shuesu is going to be our invited speaker here, and Chris will be our spring speaker. And then both of these have, let's say, a related hands-on session on Friday, okay? The 7th plenary session is going to be about sensing the environment. So self-localization, understanding if there are what obstacles or objects are on the ground, like if someone has fallen, for instance. So Antonius is going to be our invited speaker, and then Michal, who just arrived, is going to be our spring speaker. And finally, we will have the last, hopefully I will not fall. Our last plenary session is going to be about human behavior understanding. So Atice is going to be our invited speaker from Cambridge. And then Lorenzo, that will travel, I guess, on Wednesday from University of Trento, will explain the achievements on this Work Package 4. All right? And then Michal will also be here for a hands-on session on Friday. The panel session is going to be about how ready are robots to be deployed, right? What are the immediate challenges? What are the things that we need to solve? And then we will have wonderful set of panelists. Some of them are from the Spring Project, some of them are outside of the Spring Project, so you get, let's say, an unbiased view of the thing. The only change will be that Mihalis unfortunately will not be able to travel, so Mark has accepted to take his position, but this happened this morning, so I didn't have time to change the slides. Then there is an outstanding poster session with 15 contributions. I highlighted here in green what I thought was the most important part of the title, but this is like a personal appreciation, so you might not agree, especially if you are one of the poster presenters. But this is just to show that that we are also very happy that you are contributing to the school with your topics and with your interests, all right? So that's also important because we might have a specific view of the thing, especially after 4 years trying to do something, right? But now you come with fresh ideas, fresh blood, and this is also very important to foster new research directions. So we will be very happy to discuss with you about your contributions. Then we have the social program on Thursday afternoon. So you have two choices, either visiting the, let's say, the historic downtown Grenoble, that's at 2, I think, and the second option is to climb to the Bastille with the cable car, right? So you don't need to walk up if you don't feel like. And of course, you have all this information is in the booklet that we have sent you, and you have registration links as well. And Mathieu has a comment or a question. Aha, only one slot left for the cable car. That's an important point. Maybe it's the most important piece of information of the whole. All right, good. So the last part of the school is going to be the hands-on session. You are going to have 5 choices, and you have 2 slots, right? One before lunch, one after lunch, right? So you can pick 2 different sessions. If you want to pick twice the same session, I say why not, but maybe it's more interesting to have to work on 2 different topics, right? So you go from navigation to LLM based dialogue manager, localization, speaker extraction, and then we also have this person manager, which is a very important piece. It's when you have all your sensing, all your sensors telling you where persons are, and if they are talking, they have to merge all this information, right? So that's what SoRAIM will try to explain on Friday. So I wanted to end up, because I don't think I will have the opportunity to do that later in the week. So I think it's important to thank those who made that possible. So we start with our sponsors. So of course, the European Commission and the Spring Project, obviously. Special interest group on multimedia that allowed that some of you had some help traveling here, for instance. The Grenoble AI Institute also contributed to supporting the school, as well as, of course, the university and INRIA, and specifically the Young Researchers program. I wanted also to warmly thank the invited speakers. Some of them travel from far, far away, like some of them from the US with 7-hour plane and 3-hour train. So we are very grateful that you put on hold your regular duties to be here and to share with us your expertise. I wanted to also thank the Spring speakers, because they did the very same thing. They put on hold whatever they have going on. They prepared a presentation to share with you, thinking what's going to be the most interesting thing that we did through the project to present to these students that are eager for knowledge. And of course, I wanted to thank the organizing committee. So Alex, Kiru, Victor, and Nicolas, because they have been working on showing you the demo. So if you like the demo, you go and tell them that you liked it. And if you don't like, you don't go and tell them anything. All right. I also wanted to thank Mathieu in the back, because he helped me a lot with the with many different details and things that I wasn't able to think about. So he was like, oh, maybe we could do that, maybe we should do that, maybe we must do that, and then we were ending up doing something. And of course Nathalie, because all the administrative part would have been a mess if I had to take care of that, but Nathalie is very efficient. So thanks all for being here, and I think it's time for questions if you have, and then the demo maybe while you set up.
Okay, so just before the demo, we will do some presentation with Victor and show you an example that what can be the navigation part and the dialogue part. So yeah, our goal is social aware robot navigation. So just we want to navigate to a specific position, to a group, to a human, or a human inside a group in an either indoor environment with static and dynamic cycle. So we have a lot of constraints. So the first one is the hospital indoor environment, because the final goal is to put Ari, the robot, in the hospital. And then we have the human behavior. So it's difficult to predict the trajectory of the human and their behavior, how they will react with the robots. And then we have the robotic platform, so the hardware and the software issue. So the GPU, the CPU, and all the bandwidth limitation with the Wi-Fi. And then of course we want to that Ari navigate in real time. So we want real-time navigation. So like this winter school, it's inside the Spring framework. So the navigation part it's at the extreme right of the overview. So we depend of all the other components of the partner. So this is a bit difficult to understand, but this overview is just to show that each color is a partner. So each partner has a specification. So the audio, the visual, etc. So if they have some issue, some noise, we will get that inside in our navigation, because we are at the end of the pipeline. So this is the array, as you can see. So for the navigation, we will use the audio. For the interaction also, we will use the audio and some cameras. So for the audio, we have 8 microphone array. And for the navigation, first we have a lot of cameras. So we will use for instance, the front stereo fisheye to detect the people, and the camera, the torso front that is looking down for the navigation. So first, for the navigation, we need to know where is the robot in the room. So we used an open source algorithm. So it's called AirTab map. So it's a SLAM algorithm. So with that, we map the static obstacle of the room. So then we know where is the robot in the room. So the output of this algorithm is a map with a pose of the robot. So we will use this map to navigate. And on the left, you show the input of the algorithm. And on the bottom left, you will see it's our lab, and on the right you have the results. So now that we know where is the robot, we want to know where are the human on the scene and from the robot. So first we need to track and detect the human. So for that we are using Fairmont. So at that time it was the state of the art on multiple object tracking. So we fine-tune Fairmont on fisheye images, because Fairmont is trained on rectify images. And we didn't want to rectify the images, because if we rectify the images, we will lose some field of view of the scene. So we fine-tune Fairmont on fisheye images, and then we can get the human on the image plane. But for the navigation, as I said, we will use this map on the right. So we need a top view scene of the scene. Sorry. So we want to know where are the humans from the robots. So for that, first on top of this tracking algorithm, we will use OpenPose. So OpenPose is just to extract the skeleton. And then when we have this skeleton, we can do a nomography between the floor plane and the human plane to know where are the human from the robot. Because we know that if the foot of the human are at this pixel, we calibrate the camera that we know that the human is at 2 meters, for instance, from the robot. So with that, we have the pose of the human, the distance of the human from the robot. And then with OpenPose, the good point is we have two points detected on the feet, on the foot, and with that we can get the orientation from the robot. And the result of that is this figure on the right. So we can project on the top view scene the position of the human. So then we are creating this social zone. So this social zone is very important for us, for the navigation, that the robot can go too close to the robot and be in the intimate zone of the human, and this is okay. And then when we project that, we run a top view tracker because we have less overlapping identity switching when we are tracking on 3D, so on the top view scene that in this plane. And then we did some deletion of the global and the local scene to not just bump into the obstacle. So for the planner, we need a global planner. So the global planner runs at every 2 seconds, so it's very slow and it's just running on static obstacle. So we will use this planner to just got some intermediate waypoint. As you can see on the green curve, we have like a TF frame, so it's an intermediate waypoint that we'll use that on our local planner. So for this local planner, we have 2 methods. So a non-learned method, so the MPC, and a learned method that Victor will present. So the MPC. So the MPC is just an optimization on nonlinear constraint. For the constraint, we have the velocities, the maximum velocities of the acceleration, and the loss. So the loss can be for instance, the loss is this map. So this is a cost map function that we will put into this optimization. And this optimization will give us the U. So the U is just the velocities of the robot to navigate from where it is to the next waypoint.
So now that we know how to navigate with a nice local planner without learning, we wanted also to try another local planner, so another version with a learning method. So based on deep reinforcement learning, maybe some of you are familiar with what is deep reinforcement learning. So basically you have an agent that gives action to an environment. The agent is in a given state, and then the environment says, okay, you have this reward based on the state you were, and you will be in the next state. So in our framework, the agent is our robot. The agent is a robot, and the environment is the room. So to do so, we implemented what we called a multi-party interaction simulator, so which recreates a room in 2D from a top view, in which you have a robot and you can have like walls and nice perimeters and even humans. So to simulate everything that happens in real life, so a social environment. So to do so, we can use several data to navigate. But basically, what we wanted to use before, Alex said that we have these kind of maps. So around the robot, you can crop like a rectangle around the robot, and in which you have a local occupancy grid. So this is this kind of thing. So you have a nice square with 0 and 1s that represents 1 represents where there is an object and 0 represents when there is nothing. And also you have the distance to the goal and the angle to the goal, because you have 2 objectives. One is first to avoid obstacles, so to detect them first and to avoid them. And the second one is to join a goal position. So for this CNN-based agent, we used CNN and we merged this information with the distance to goal and angle to goal. And then we used an autocritic framework. So this network had some so it was working quite nice, but it was not really robust over repetition, because the thing with reinforcement learning is that in your environment you have a lot of randomization, and your network might not work over repetition. So given a repetition is like what we call with a given seed. So the objective is to have for every seed the most number of seed that exists, the neural network which is the most robust. So here it was not really robust. So what we did basically is that we pre-trained our encoder in an autoencoder to reproduce our occupancy grid here. And so this is sort of pre-training. And then while predicting actions at the end of our neural network, we froze this encoder so as to have a network that understands a bit better and is able to reconstruct our occupancy grid. Something important that I said before is that it's an end-to-end learning, meaning that you have inputs that represents real life data, and then the outputs are the speed, the forward speed, and the angular speed. So this was working also nice, but to be honest, there was a lot of people who were doing attention, and I was a bit jealous of these people. So I was like, I want to put attention in my thing. So instead of pre-training everything, I just put a self-attention layer. It's like from the paper called non-local neural network. It was also used in the self-attention GANs. And it appears that, so in blue, you have the rate of goal which was reached during the test episode. In blue, yeah, sorry. And in green, you have the third neural network performance, and in orange you have the second neural network performance. So here it reached the goal asymptotically quite fast over episodes. So it means that in our case, this self-attention layer was working quite well. And yeah, you have other metrics. Here you have the collisions over episodes, so it reached 0. Fortunately, our robots doesn't collide anymore during the training in simulation. So the goal was reached and we don't collide. So everything should be perfect. These are the results of our simulation when we do some tests. So you can see you have a start position there and a goal position there. And depending on the 3 architectures, which have at the end, like the trajectories chosen are not the same. You can see somehow that the one with which was trained with attention, with our attention layer, has sort of always the shortest path, which is nice. So one thing is that it's all in simulation, but we don't want to stay in simulation. We want to have it on our real robot. So we used this ROS thing with a nice software with basically I trained it, instead of training it in a given environment that doesn't really look like what AirTab map look like. You can see that this map is a bit much more noisy compared to the perfect thing in simulation. So we trained our agent in this virtual environment. So basically just the same environment that happened in real, but we take the map and give it to the agent. And I'm not going to show today a demonstration on reinforcement learning for several reasons, which are here. First reason is that reinforcement learning, sometimes in simulation, you end up in states, in some states, and the episodes are stopping at a certain distance of obstacles. So that's how the agents, and when the agents in simulation collides with an obstacles, he receives a highly negative reward. So that's how with the training it understands, okay, I don't have to go into obstacles. But in real life, the robots can collide to obstacles. So the thing is that in real life, the robot can ends up in some states that it hasn't seen in simulation. So basically, you have to sort of say to the agent where to start and where to end. So this is the point of this red zone, and you really have to say how far from obstacles you have to go. Like you can see here that the zone is reduced. At first we use this kind of zone here, but it's really far from obstacles, and all the white parts between obstacles, between the black part and the red part, is like states which were not seen during training. So the agents struggle a lot. Another huge thing, a huge problem facing when we are talking about sim to real, is the fact that our robot has a certain inertia and acceleration that might not be included in our simulation, that we didn't thought about. Meaning that if the robot is static and then the agent say, okay, now I want to go to 0.5 meter per second forward in 0.1 second, then it's almost impossible, because you cannot, the motors are not like nuclear, or I don't know, but this kind of acceleration cannot be reached. So it's like some constraints that we still have to consider, and yeah, and also the computation time, because as Alex said, our pipeline is our platform or simulation, like navigation, is at the end of the pipeline, and the loop of computation between the moment we build the maps and the moment the actual speed is predicted, there is a bit of delay. So this kind of delay has to be taken into account also. And that's the end of our stuff, I think. Yeah. So we can do the simulation, I guess.
Good afternoon, everyone. So I'm Kiru, and I'm going to give a small overview of the conversational AI that we have deployed in our social robot Ari. So conversational AI is what makes Ari from a working robot to a fun robot. So today I'm going to give a engineering perspective on the deployment of the conversational AI, and also the challenges faced while deploying it on the social robot. So our goal is to have a context aware and domain specific conversational AI within a social robot. So our RE is meant to be deployed on a hospital platform as a medical assistant robot. So what do we expect as a characteristics of an appropriate conversational AI? So it should be domain specific. So here our RE is meant to be a medical assistant. So its responses should be relevant to its role, and also short. So it should have a short response time. Also it should have multilingual capabilities. Right now RE can converse in French as well as in English, and we have to maintain the privacy and the security of the data of the conversations we have with the patients or the users. And it should be capable of integration in a large robotic applications such as our RE. And what are the constraints that we face? It's mostly with the implementation with the ASR, which is automatic speech recognition, and the TTS, which is text to speech. And what are the common challenges? It's when there is an error with the ASR listening. Sometimes it only takes in the part of the sentence that you say as an input, and that's not a right prompt. Also it may take a different word than what you actually said. So it's some of the errors that are encountered with ASR. And with respect to TTS, if the response is too long, with the voice of RE, it is sure to make the patient to sleep. So we need some short responses. And what are the additional requirements that we need for a social robot like RE? So it should know when to talk and when not to talk. So while it is having a conversation with the person, it should not overlap with while the other person is speaking. Also, while navigating, it should not speak, because while navigating there will be noises from the motors which will interrupt the good working of the ASR. So it should not talk while navigating. Also, it should be able to integrate with the other modules like navigation or as a behavior generator. And we also integrate in navigation, like if you have the map of this room, so it should be able to navigate to exit from our voice commands. And also it should look at the person with its head movement to make the conversation more natural. Also, when we are having a long conversation, it should be able to retain the context of the entire conversation while not having the entire conversation history as a prompt, because it's going to delay the response time. So also, since RE is a robot that could actually navigate, we should have a emergency stop command through voice. And these are the models that we use in RE. For ISR, we use NVIDIA Riva 2.7, which is a combination of self-attention modules and convolution modules. And for TTS, we use from Acapella group, which is by multilingual. Right now, it can converse in French as well as in English, and it has different voices, and it is built in on the robot. So the default LLM used is from Heriot-Watt University, which is Alana plus Rasa, but we don't know the internet resources here, so we developed a small LLM. We are right now using a open source LLM that runs locally on the GPU, which is Vicuña 13B, which is fine-tuned and packaged by LMSys, which is actually from a collaboration with UC Berkeley. And right now we are using LangChain platform, which is a platform framework used for developing applications with LLMs. So it provides additional functionalities than using the OpenAI platform or something. It can actually we can actually able to explore different LLM models with a single framework. Also, it can give additional functionalities like RAG, which is the latest one, retrieval augmented generation, where you can give the details of the place or the university or the hospital, and it can answer from the real-time data. And here's where our main focus of work. So at first we gather the sound of the user through the 4-channel microphones available on the front of the RE. Then we get the direction of the sound to locate the human, also to make the head rotations. Also we get the sound waves, which is you processed by ASR to get the actual sentence that we said. And then we are using some trigger words for different purposes to navigate and for generating the certain behavior. So at first it will it detect for any trigger words in the sentences from the user. If there is any trigger words to navigate or to stop the navigation, it will do that. Or if it is to start a conversation or to end a conversation, it will do that using a behavior generator. And also, if when there is no trigger words in the sentence, it moves on to the prompt generation, where we do some prompt engineering to keep the prompts small as well as the response small, so that we get a faster replay. So once the prompt engineering is done, the prompt is sent to the LLM, which is Vicuña 13B. Then the response is generated from it, and then it is sent to the TTS. And with the response as well as the language of the response, it is sent to the speaker, which is set by Ari. So before going to the challenges, we'll see some demos.
Hello, I am Ari.
Hello, I am Sheldon. Who are you?
I'm Ari, a medical assistant robot. How can I help you today?
How can you assist me?
I can assist with medical tasks and provide information.
I have a terrible back pain. Which specialist doctor should I visit?
They should visit an orthopedic specialist.
Okay, could you book an appointment for me with them?
I'm sorry, I am not able to book appointments.
Okay, could you suggest me some over-the-counter medication for this?
ibuprofen or acetaminophen.
Okay, could you guide me to the sink?
Moving to the sink. Reach the sink.
Do you remember my name?
Yes, your name is Sheldon.
What was my last question?
Your last question was, can you remember my name?
Okay, thank you.
Thanks for coming. Have a nice day.
Ari, stop moving. Ari, stop moving. So, as we saw in the video, there are some challenges we face, mostly with the ASR. Sometimes it doesn't take the right word we say, and based on the acoustics of the room and the sound reverberations, it can take in wrong inputs. Also, it can, when we pass in between a sentence, it could take that as an input, an incomplete dialogues. And also, while it is navigating, it can't take inputs because of the motor noises. And also, when we use LLMs, especially the local GPU ones, so it is a high GPU consumption. Also, right now, even if there are two persons conversing with them with Ari at the same time, it can consider both of them as a single person, not as a different person. And if once the conversation with Ari is started and the two people are started conversing between themselves in front of Ari, it will take every sentence as an input to Ari. So that's a problem with that. And there is a hallucination, which is a common problem with all the LLMs. If we ask Ari right now, where is the restroom, it will give some random instructions, like it is in the front of a hall or something like that. So that's a hallucination. And right now we are using trigger words, which is efficient for us, but not convenient for the users, because right now if we ask how do we stop bleeding something, it will take it as a command to stop the navigation rather than the actual response. So we might use more LLMs in parallel so that it could know the intention of the user. So these are some of the challenges we face right now, and thank you.
Now we will show you the demo. So just for you, on the top left is the input from the torso front camera. So this one, as you can see. So this one is just used for the navigation, and it's for the navigation we are using the infrared camera from this camera. And on the bottom left, you see the fisheye with the tracker and the skeleton extracted. And on the right is the output of OpenPose with the top view scene. So you can see I'm in blue with my social zone. So if I'm with Victor, down now we are inside a group.
Yeah, the group is there.
Yeah, and then we are two isolated people. Yeah. Yeah, we see the group, yeah. And now there is no more group. So, yeah, this is an issue because you see Victor switches an ID, so now Victor is doing a group with the new Victor. So there is some issue in the tracking, but yes, just to show you. And on the left, you will see the dialogue part.
So someone was asking, is this live? I heard someone. So yeah, it is live, but we are not storing anything, right? So this is just tracking, and then we are throwing the data away. So there is no issue with that. All right, just for you to know. So, what are you gonna show us?
Navigation and interaction.
Okay, so that's going to be a combined demo between navigation and interaction, and we have a question. So the question is about the eyes of the robot. If it's a random movement, yes. The answer is yes. Okay. The head should be pointing towards the person or the speaker. But yeah, the eyes are pretty random. Yes. The microphones are the LEDs that you see here, yeah, in the belly. And then I now probably should stop talking, otherwise it will recognize what I'm saying. So the way it works right now is that the tracker is outputting an ID, that's a number, whatever. I think Victor has 54 or something like this. And that's what we are giving to Ari, right? But of course, this could come from whatever thing, like the saddest person in the room, or whatever you wanna extract this information.
I'm sorry, but I am not able to provide medical advice or treatment. Please speak with a healthcare professional.
Okay, anyway, can you guide me to the exit?
Moving to the exit.
Yeah, you can see that given we have a high latency, we decrease the velocity, so that's why the robot is very slow. But in the future will be faster. We hope. So yeah, the robot is guiding Victor to the exit, basically. Yeah. So we fixed the velocity at 0.1 meter per second, so it's very slow. Yeah.
Reach the exit, 1 meter per second. Thanks for coming. Have a nice day.
And then now the robot will go back to the starting position. So when you're starting there, yeah, then you can try the stop command.
Stop moving. Stop moving.
Good.
Stop moving.
Okay. Now it's good. Sorry. Yeah, that's done.
So you can see that Adi, as any robot that has to get the proper name robot, is a bit stubborn, right? That's what it wants, not really what you tell it to do. But yeah, I mean, this might seem, let's say, a little bit easy or simple, but it actually takes a lot of effort to make it work in a real platform. And what you also should know that might be interesting is that we are not here. We are not located in the campus. So it means that, okay, we moved the robot last Wednesday and we worked, we just made sure that the demo was working here, but we didn't have like months to fine tune the things here, right? So this is basically what we get after so many years of work, and we are very happy that it actually works in an environment that we never, prepared for. So there is a lot of time for questions, I think, because it's like yes. So I think we will have a microphone from yes.
If you wanted to talk with him from your microphone, would it be disturbed by the fact that there are two source of sounds, or even four? I don't know.
I guess the right person to answer the question is Sharon.
Hi. We have speaker separation as well implemented. It's not deployed here, I think, yet, but we have speaker separation as well, and also we have something that we call speaker extraction. If you know the person in advance, or you know some of its audio ID, then you can extract it out of a mixture of several speakers, and then the robot will decide, or the algorithm will decide, if we just need to reduce the noise or to separate the speakers, and then apply it, and then this will go to the SR. The SR client, by the way, we can have several clients working together. So if there are two people speaking and we separate them, then we can also transcribe both of them. This is still a bit ongoing, but it is already working, but needs a bit more improvement. I will explain about it during my talk a bit.
Yeah.
Thank you. Thank you. Hi, really nice job. It's really great. Two questions. For the exit, did you have to enter a coordinate for the rope? Okay, you did. And then the second question is, how do you retain the past knowledge? Like, is it stored? Because it sounds as if it's not stored, but it seems as if it is.
You mean for the dialogue?
Yeah, sure.
So right now, the motive is to keep the size of the prompt that we give to the LLM short and precise. So every few back and forth prompt and responses, it will make a summary of it. So to keep only the relevant information, like the name of the patient or what was the detail they were asking for, rather than the entire conversation. So yeah, that's how we maintain the yeah, it doesn't remember the exact words that it's said in the previous conversations, previous sentences, but it will remember who you are, what were you asking about, and everything, the relevant information. Sorry?
Main information.
Yeah, the main informations.
Thank you. How long it will take to map a room?
I think it's a matter of 10 minutes.
And it can move from one room to another, like following an highway, so it can move from in a whole building, or?
If you map it,
Yeah.
yes.
Okay.
I don't know about the lift.
Okay.
If it has to take the elevator, I think you need something else. Yeah.
No. Well, it can.
For the mapping, one big detail is that the camera that has the depth is the one that looks down, so the top left that you have here. So here it's just the infrared result, but it's also like Ari has also a depth camera there. And so because you're looking down, if you have, there is another room there, we try to map. If you have reflections because of the light of the outside, you have a lot of noise in the map. So basically the noise looks like little dots, like black dots, which should not be there. So you have to go again into this area where there is nothing and remap these kind of zones. So in a room like this where there's no terrible stuff for AirTab map, it's quite fast, but it really depends on the environment. If it's outside, we never tried, but yeah.
Yeah, basically you need a lot of texture and obstacle. That's much easier to map.
Okay, thank you. For the demo, I did a lot of demos, so I know what is the job to do such a demo. So well done. Just some question about the sensors. There is no LiDAR. Was your choice, or it is by design at the beginning of the project?
No, I mean, we took the robot like this, so we didn't modify
Okay.
the robot. So
Same
the robot is built like this, so no LiDAR.
Okay. And same for the microphones. It's weird to have 8 microphones and no microphone in the back.
Aha.
So this is a 4 microphone array. We spent maybe 6 months trying to find out how to put this microphone array or like a similar one into the robot. And the problem is that there are, I don't know how many different physical, electronic and mechanical constraints. So at the end, like the belly, it seemed to be like the only feasible option in the time that we had, so that we could then have the robots manufactured and then deployed, like sent to the partners, and then we could start working. Yes.
Yeah. So thank you for the question. So it's not the ideal place.
Yeah.
So we have ears on the head, which is a good idea. It's better than in the belly. The 4 microphones, also the position of the microphone is not good. So it's parallel to the body of the robot, which doesn't give us too much spatial information, which we need. So most of the algorithms that we implemented eventually were single microphone. So we do not utilize all 4 microphones. Some of them for localization, for instance, and so on, we need more. But we also developed multi-microphone, but I guess that the end product will mainly use the single microphone algorithm. So the enhancement and separation and some activity detection will be single microphone. So this is not ideal, but it's still working. There is some type of spatial information due to the fact that due to the body and all the reflection inside the body, it gives some differences between the microphone. So we can utilize it, and it is working, but the single microphone is more robust.
Okay. A very short last question. Is there noise in the microphone coming from the robot itself?
Yes.
Okay.
Yes.
Thank you.
The motor is a problem. Yeah.
Hello, thank you for the demonstration. I would like to ask if the robot is able to call emergency help if the person faints or there is a sudden change. Because in a hospital, for example, in the ER, it would make sense for the robot to be able to call the code blue.
So I think calling like the emergency, some sort of emergency response, that is not difficult, in the sense that it's like a technological model, like some sort of code that will call some certain API. So that is, I don't think that's difficult to do. I think what is difficult is to develop something that is able to properly judge when to trigger that. This is much more complicated, and no, it's not able to do that right now.
I think on Thursday we might have a talk about fall detection, that when people are falling and the robot detects it. And I think we will.
Thank you. It's mostly a question about LLMs and conversational AI. How much is handcrafted and how much is LLM generated in the responses that you get currently?
Okay, the specific integration with the other modules for the navigation, to start the navigation or to stop the navigation, it uses the trigger words, which is what we do through the hard coded. But rest of us is through prompt engineering, is not engineered by us. If you give the right prompt to the LLM, it will give whatever the specific responses and the relevant responses that we want. So only the trigger words are mechanically done by us. Other than that, it is truly from the LLMs.
Okay, so I guess that you have some sort of initial pre-prompting to give some instructions to the LLM to, let's say, mimic a person from the hospital or something like that, or?
We kind of set the nature or behavior of the LLM, how we should, in this case, when we ask who are you, it says I'm Ari, I'm medical assistant robot, which is due to the prompting. So apart from that, we also give some instructions to keep the response short and precise and relevant to the specific role. So it's more of the prompt engineering than mechanically changing what we need the responses. Yeah.
Okay. Thank you very much.
Yeah. Sorry, just because we have the microphone. So Kido, thanks Kido, replied for what is running here.
Yeah.
But as Kido mentioned, in the hospital we have like a dedicated internet connection, so we could actually use what is developed in Heriot-Watt, and I think that's what Daniel is going to.
The robot in Sprung has, we give them a lot of information about the hospital that's being collected by Lorian and other personnel from APHP. So he knows about, I don't know, the operation of the hospital, the waiting times, where's the cafe is located, the opening times, all those kind of information is given to it, and the output is extracted from that prompt. But also the LLMs itself, they just generate. Like sometimes the answers are incorrect, sometimes it hallucinates certain information, but we try to make it keep to what is as like known facts about the hospital, to only answer when their questions are about the hospital, to stick to those. When people ask about other random things in general knowledge, then the LLM is freer to come up with answers and be more social and welcoming. But yes, it's a mixture of both, and they're always going to, I mean, eventually they're always going to come up with their own thing. You try to force it to keep accurate, but yeah.
Yeah. So is it, sorry, maybe I'm using too many questions. Is it in the future plans to make it able to answer, let's say, specific medication for very simple problems, I guess, or some specific things?
The
And
robot,
yes.
as a safety thing, the robot should never tell you about medication,
Yeah.
just because sometimes they will come up with hallucinations. So that's
Yeah,
very hard
exactly.
to guarantee. So as a safety thing, it should never give you medical advice or things about your diagnostics, or like it should never tell you, yes, take ibuprofen. Even if taking ibuprofen, it should be fine, but it should never say those kind of things for safety, not for.
Thank you very much.
Just also on that, there's another layer to that. It's not only the technicalities; it's also the ethical setup in which the experiment is done, and in which the robot cannot have access to the medical information about patients themselves, right? So ethically speaking, we cannot store information that is related to the medical situation of you, let's say. And so in this case, it's even if technically it was possible in the setup that we have, it would be not possible experimentally speaking because of the ethical principles.
Hi, I think I have 3 questions. First one would be, did you try some other ASR architecture aside from the conformer one? Did you use something like, I don't know, Whisper or Wave2Vec or something else? Like it may be better with those problems you mentioned.
Yes, we did try, I think, every commercial ASR that works streaming, and we get that the Riva conformer one is the best in French right now. The Whisper is okay, it is quite slow. The Google ASR is better, but it kind of stores your data always, so it's not a good use for a medical assistance, and that's it.
Did you maybe try distilled versions?
No.
Because from what I know, they are like superior with hallucinations and... Okay. Distilled versions of Whisper, it's like 10 times smaller the size. You said it's really slow, but performs similarly and has less problems with...
We did hear about them, but I think they don't perform quite well with streaming ASR.
Okay, okay.
The conformer is it's like it's not only the ASR; it has a language model for predicting the next word in streaming.
Okay. Thanks. Well, the next question would be related to navigation. You created your own navigation algorithm, right? Like an autoencoder?
For the DRL.
Yeah, the reinforcement learning. Yes. Yeah.
Did you use something, some classical algorithm like DWA, DWB? Did you try those? Like it may be easier to program and move the robot and it would be faster? Maybe.
Well, okay, so the reinforcement learning that Victor showed is currently, that was not what was running on the robot. Actually, what is currently running on the robot is a more classical, like a model predictive control algorithm.
Which one?
Well, I would, I don't know if we have a name for it, but I will talk about it more on Thursday.
Okay.
But it's a classical model predictive control, so very classical control, yeah.
Okay. But what was the motivation for the reinforcement learning algorithm?
Well, the reinforcement learning is a bit more like research-wise, you know, to look into the future, because in the future you would like that the robot can also learn to navigate in new environments, or especially to learn to navigate in new contexts. Like, what if people need a different personal space, or you know, then you would like that the people maybe you can read their reaction to ARI and use this as a reward signal, you know, how well does the robot navigate around me? And then the robot can learn to improve its navigation. And for this you need a learning algorithm, so that would be then more reinforcement learning.
Okay.
And the inference of the RL algorithm can be 100 Hz or 50 Hz.
Yeah, it's,
I don't know.
Basically, it's just an inference of a neural network, and the architecture is quite small. So it just takes 2 milliseconds to taking data and just predicting velocity. So it's really fast also.
Okay. Yeah, it makes sense. Thanks. And the last question is related to the fisheye. You said that you would lose some information if you straightened the fisheye. Like, why don't you straighten the image?
Yeah, if we rectify the image. So this is the 180 degree freedom, this view, this
Okay.
fisheye. And if we rectify the image, we will lose part of the field of view. And the obstacle and the human will be distorted. So at the end, you will need to retrain your Fermat algorithm, so your tracking algorithm on rectify images will be the same issue.
Oh, I thought that like it would be more distorted if you leave the fisheye as it is, the fisheye view. Like now you have like more of an arch shaped of a leg
Yeah,
hand.
but
or
this one is not so distorted. If you
Okay.
rectify this one, it will be very distorted. Yeah.
Okay. Okay. Well, thanks.
Yeah.
So just quick question. Is it because that instead of looking 2D, it looks more 3D? Is that why? For the image that he was just saying, the fisheye image, it looks somewhat, because you know if it's a pixel, it's just flat. So I'm saying that because I see some curve, is that why this is preferred?
That's just a distortion of the lens, but it's still a flat image, right? There is no 3D on the image here.
Thank you so much for this very interesting demonstration. I wanted to ask you about the action recognition, or in terms of like the Ari understanding what's going on like through his camera. So what kind of work are you currently doing within the team, and where is it in this, if it's there in the future scope? Because it's interesting to, of course, for Ari to understand what's going on to the patients as well.
Okay, so I think there are various ways to answer that. So ones more on the social side. So part of the actions are like being together in the same conversation. So that's something that you have seen already. In the project, we have also worked on emotion recognition from like facial expressions and from speech. So I'm pretty sure that maybe on Friday morning you will hear a bit about that, also with Atice. I think we have also worked on like things, are people wearing the mask or not wearing the mask? For instance, that was very important like a couple of years ago. One of the difficulties that we face is that if we want data from the hospital, like to actually evaluate, this is very hard for like a gazillion constraints, right? So usually it's easy to have like some examples to evaluate, to test, but then to train, it's actually super hard because you have very, very few data. So it is true that one of the questions is, how do you adapt something that you have pre-trained, like an action classifier, for instance, into the classes and into the kind of things that you see in the hospital when you have so few data, right? So this is clearly an open question, and there has been work in the project, but it's definitely not solved.
Yeah, I understand. Thank you.
There was Mathieu.
Hello. Yeah, thank you for this nice presentation. As I can see this is a medical robot. This will be deployed in a hospital. So did you do any test of how this SLAM and navigation algorithm will perform in dynamic environments, or this is some of the future tasks?
So in the hospital, we have a constraint that was given by the ethics committee, is that the robot cannot see people that did not agree to interact with the robot. And I repeat, cannot see people that did not agree to interact. It means that even if they don't interact with the robot, but the robot is wandering around, right, then there is a problem. So it means that we cannot really test this. I mean, we can test it in the static environment, and we can be like people in the project there, right? That's fine. But that's not really, like, then it doesn't, why doing it there, right? It's not really important. So that's why it would be great to actually test that. But right now, with the let's say ethical framework that we have, it's not really it's not really possible. Okay. There was a quick combo question.
Sorry. Could you please elaborate what you mean by a robot cannot see? So it treats them as an obstacle, or just doesn't detect them?
Sorry, yeah. It means that if people did not agree to interact with the robot, they cannot be in the field of view of the camera. So basically, the experiments that we do in the hospital, it's in a dedicated room, so that we are sure that no one just wildly appears there, and then the experiment has to be cancelled, basically.
All right, thank you.
Just to clarify, it's not that it cannot see it; it's that legally it is not allowed to see it.
Thank you for the talk. So as far as I could understand, so you use MPC for the navigation, generally I mean, but you give MPC a cost map. So this cost map is extracted from how to approach people from Trung and NGO. I assume this is Proxemics. Yeah, okay. So did you do a comparison between that navigation with MPC and reinforcement learning in simulation, maybe?
I think you do.
Yes, and well, in simulation, reinforcement learning is faster because, as I said before, the inference is much faster, and the results in terms of path are quite comparable, quite the same. Our objective is to compare it in the real robot, but yeah, in simulation, basically the calculation has already been done in the training, sort of. So the inference is like really fast, and the results are, in terms of trajectory, are quite comparable.
Okay, thank you.
Thank you so much for the demo. I really enjoy it. And I have a couple of questions. So the first question is about the video that you saw in the slides. And my question is how, when you mentioned to the robot, go to the sink, how did the robot relate that information with the visual information, and then the robot went to the sink accordingly?
Right now it's not that complex. Once we have the global map of the any room,
Yeah.
so we set the coordinates and the keyword for that, the trigger word for that. In that sentence, guide and the sink are the keywords.
Yeah.
So if you say guide, and if the sentence has any of the coordinates that it has, like exit or microphone or something like that, it uses the trigger word to go to the specific coordinate.
Okay, so you assign that coordinate to the word sink, basically.
Yeah.
Okay, yeah. My question was more like, oh, maybe has some semantic understanding of the environment, but that's potential future stuff.
Yeah, not right now.
Yeah, that's quite complex. Yeah, that's why.
Yeah, I mean, I guess part of the answer can be there by the VLMs, right? Visual language models, for sure. You still need to be sure that you will detect the object that you are interested in, so that's not quite obvious. And I guess that basically just reinforces what I said at the beginning, that when doing things like this, a system that does many different stuff, you need many different people on board, so that you are sure that you are treating things properly, because each of these things has a very specific challenges.
Yeah, and one quick question. How are you using the output of the tracking models and the pose models? Maybe you mentioned it, but maybe I miss it. So you have there like a lot of, poses, right, and people that is being detected. How are you using that for the demo? Like the output of the detector and the pose estimation.
So basically, if now I just appeared in the local map, right?
Yeah.
And basically the position of in the image is triangulated, because we assume that people are standing on the floor and not flying, so that should work. So you can get the depth, right? And then with OpenPose you get the body orientation, right? And this is how you later can decide, like, if Alex would come here, right, then we are in the same conversational group, but if I am here, then we are not in the same group.
Thank you.
Yes, but it would put you much far away. That's all.
It's okay. Oh. Yeah, okay. Here and then I'm moving here.
Thank you for the talk and the demo. I have a question on the deep reinforcement learning approach. You use the self-attention layer. How has the self-attention layer improved the performance of the model? Did you do any statistical test? Or?
Not yet. First, when I saw it was working, I tried to understand why it was working, and because now it's important. Like, neural networks can be a black box, but somehow you can understand. And then, if you look at let's say the pink thing is the local map of the robot, it sort of makes sense because a CNN is good at looking into local area, like with the kernel operation. It's good at looking in, for example, correlation into a local area, but not correlation between area which are from one point in a map to another point. So with navigation, it sort of makes sense to look at different parts of an image which are not close. And we think this is how self-attention helped in a way. And this was also the motivation of the paper, which was called non-local neural network something, saying that an image might have interesting information which are not close in the image. Like if you have an image with a bird and another bird or something, you would like the neural network to focus on different parts. And we think that's why it's working a bit better. And also it's understanding a bit more the image The point of this is that we train the CNN with a loss which is respective to the reinforcement learning problem, and not, for example, reconstructing loss like in the pre-training. So the output of the CNN is also biased by this loss, which is just reinforcement learning loss. And maybe the self-attention model helps to say, okay, we have this loss, but you have to reconstruct a certain map and to look also into different places in this map. So we think this is how it's done, sort of, in the self-attention layer.
Okay, thank you. That's
Hello, thank you for your interesting simulation. So my question is that I see you designed the robot with hands. So my question is, do you have like maybe features that you can use like with the hands, or maybe like future plans, maybe you can like shake, or maybe it can carry stuff?
So we did not design the robot, right? So PAL Robotics did design the robot. We did not use the hands other than for the visual appearance, right? I think it does make a difference to have arms and hands, not to have them. I think right now Ari is not really good at carrying things. I think it can take like maybe 1 kilo or no? Huh? Yeah, it's like a tennis ball, right? And yeah, and that's all, right? But they yeah, of course they have motors, and you know it can move, but it's not really made for like carrying things. I think they designed this more like a social interaction platform, right? So they have other robots that are meant for that. So.
Actually, I have another quick question. For now, I mean, Ari talks in English language, right? Is it possible to also talk like in other language?
Yeah. So it has. So we are using this a cappella as a text-to-speech. We tested French; it works well. There are other languages. I think I don't know how many, like 24 maybe or something like that. Yes, that is my next point. Is that maybe Ari can speak in different languages, but when you change the language, you have to change the language 3 times for the ASR, for the dialogue manager, and for the text-to-speech. And it happened to us already to change only the text-to-speech to put it in French, and then it would speak English with French accent, which was very funny, right? But you have to make the switch to the whole system, right? Otherwise, you get half-half.
Thank you so much.
Yeah, I noticed that it doesn't have a back camera and that it didn't actually recognize people that were standing behind it, if I saw it correctly. So how do you deal with that issue if it navigates, that it doesn't accidentally like knock people over that are behind it?
So Ari has a few back cameras actually. So it has one fisheye here and a stereo fisheye, right? We are not using this right now on our demo, but it's totally possible to do that to avoid obstacles, to do whatever you want. But yeah, for now we are not using that.
I have a curiosity. You put Ari with patient, right? What kind of conversation they usually, how they interact with the robot? What kind of question they ask about the interaction? I would like to know more.
Yes. So I'm going to give the microphone to Lauriane because she's the one standing with patients and the robot. Is that okay?
So one kind of question patient ask. Some patients want to ask about their appointment. For example, what time is... sorry, my English is very so bad. So, for example, c'est difficile. Yes. Sorry, it's really complicated to. Ouais, mais même en français, là, j'ai tout perdu, là. Par exemple, à quelle heure est mon rendez-vous?
So, for instance, what time is my appointment? How much time will I wait? When I can see the doctor? What is the restroom? Can you take me to the restroom? Yes, the time of the meal time. Where is the cafeteria? Where can I get a coffee? It's like very practical questions, let's say, of how is so in the daycare hospital. Basically, patients go there the whole day, and they might have like 2 or 3 appointments. So there is a lot of time spent in the waiting room in between appointments, right? So they want to actually understand, how is the day going to be, right? So the question was, are they reticent to the robot? And Lorian says no directly. So
Maybe 1 or 2%, but it's because they're scared. It's not. I think it's a question about habitude.
Yeah, being used to.
Being used to. So, but a lot of older adults like the appearance of her because it's arranged like the sun. His height is not a problem for other adults. So no, they're like. I surprise because I have habitude of now of robot very small, but with Harry, it's a great experience.
Another question, sorry. So Ari stay basically in the hall of the hospital, right? When people stay to wait in the wait room. No, I don't know in English.
Yeah, the waiting room.
The waiting room. If people see like humans and then the robot, and they have to ask something, did you notice if since humans are always moving around because they have stuff to do, did you notice if they tend to go to the robot instead, or they prefer to wait for the human to talk to them?
So this is something we cannot measure, unfortunately, because, as I said, Ari cannot legally see persons that did not agree to interact with. So it means that people that go into that room where Ari is, they already know there is a robot there and they agree to interact with. So we cannot measure if they are happy to interact with or not, if they are willing to interact, because, a priori they already said yes and they confirmed this yes the very same day. So that is a limitation of yes.
Thank you for your presentation. My question is regarding the security and the privacy challenge. I want to know if this robot is doing any safeguard of the patient data, and if so, how do you deal with how do you preserve the privacy and of the medical record, for example?
Okay, so there are, I think, several ways to answer that. The robot has no access to the medical information of the patients. So it just has no access to that. So for this, there is no way of possible conflict in this regard. Now, for the privacy, this is why the only thing that doesn't run on the robot or on the computer that is sitting there, it goes, in case of the hospital, it goes to a partner of the project, which is Harriet Watt, right? But we don't use any cloud services like Google or Amazon or whatever, right? Because everything, we need to be sure that there's not going to be any violation of the GDPR or the privacy regulations, right? So that's the other.
You don't need to gather any sensitive information from the hospital.
We cannot. Right. So we cannot react to, I remember you from last time, for instance. This doesn't happen, right? There is no last time, right? Or I realize that you tell me that you have back pain. It doesn't happen either, okay? So there is no, yeah, I hope it's clear.
And just a question about the dialogue. Wasn't the dialogue over when Ari said, thank you for coming, but then he could still say stop moving. So anybody can say stop moving. Did a new dialogue started, a new interaction, or with the same interaction?
So the stop navigation command doesn't depend on any other dialogue part. So in between the dialogues, while it is navigating before the start of the conversation, after the end of the conversation, it still works because it's an emergency command. So it doesn't rely on any other parts of the dialogue.
Thank you.
Hi. Why have you decided to name it Ari?
So, Severin from PAL Robotics just arrived. And I will give the microphone to him.
Hello. There is a good reason. Now I don't remember it. Harry stands for assistant something related to healthcare. I will check and tell you. But yeah, that was the name of an acronym of a project that took place in the region of Barcelona around building up an assistant for healthcare in the region. And ARI was the acronym of that project, but I just need to check what it is now.
Okay, thank you.
My question is about interaction between, for example, and the hospital. If several people try to talk to Ari, what could happen? For example, if someone talk to Ari and someone else, hey Ari, can you help me? Da, 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 da. I don't know what could happen in this case.
So one start of the answer was already given by Sharon by processing different speakers, right? That's the first step you need. And that you need some sort of dialogue manager that is able to handle like the fact that there are several people in the scene. So I will softly handle the microphone to Daniel.
Like we are using it in experimental conditions where not random people will be shouting from somewhere else. So now we cannot handle it. Now if he listens, it will assume it's another person that was talking with Ari as part of the conversation right now. That's what will happen. And it will include it as part of the ongoing interaction. So it will try to help it, no, if that's the question. But we are not handling the case of, once we are in an interaction, we are not handling right now what happens with random interruptions to it. But yeah, that's further ahead of where we are now.
Okay, thank you.
What we are trying to measure right now is if Ari is able, if there are two people speaking, right, to understand, are the persons talking to Ari, are they talking between them, right? Because right now, if you are like two people in front of Ari, as it is right now, it will understand that you are always talking to Ari, right? So you are saying something like, see how funny is it? And then he will understand you're talking to him, right? But you're not talking to Ari, you're talking to your colleague, right? So that's one first step. And if we manage to do that, then maybe in the future we can try to identify, as Daniel was calling them, like random interruptions.
Yeah, thank you. And a last question: do you think in the future, for example, to implement this possibility to recognize emotional cognition of people on whatever the group or for one single person? Or
yeah, so this we have done some work on that, both with facial expressions and speech, so from speech as well. What we do observe, and I don't know, maybe Sean will be able to add something on that, is that in the data sets, the emotion, like in the data sets that we learn from, the ones that are available, the emotions are really intense, super intense. people in the hospital, they don't have, or even like in the real life, they don't have such intense emotions. So a classifier or a recognizer trained on those data sets, like most of the time sees our facial expressions are almost neutral, because we are not like super smiling all the time or very sad all the time or very angry, right? I mean, these very intense emotions do not happen all the time in our regular life. You want to add something more?
So this is indeed an issue, of course. Usually the databases also classifies the emotions into several emotions, like 4 or even 7. We probably will resort to 2 emotions, like positive and negative. And if it's negative, so the robot should stop the interaction, and if it's positive, it will continue. So that's what we will do. It's still a question, especially with elderly people, and especially with people that may come to the hospital which have some type of dementia. Their emotions are not as strong as in with regular people or healthy people. So this might be an issue. We do it also from visual and from audio. We didn't merge the decisions yet, but we are going to do this very soon.
Just a question about ethics and legal issues. So you mentioned that you were not allowed. Yeah, I'm at the ethics committee of university, so I need to ask that. You mentioned that you are not allowed to have people that did not accept to interact with the robot in the field of view of the robot, because you are keeping the data, right? But it's not a legal issue, it's an ethical decision from the ethics committee from INRIA.
Not from INRIA, from the Comité de Protection de Personnes. So that's a French.
You are in the hospital,
yes.
So you are in a CPP world,
yes.
Not only an ethical committee.
Yeah,
okay.
Yeah. So just for those who might not know, so the Comité de Protection de Personnes, it's the People's Protection Committee. It's a French wide committee that actually takes decisions or like put some legal and ethical framework to certain experiments. So those are the ones that decided the framework of our experiments in the hospital.
Okay. Because there is no reason to do so. My car is filming people and will brake if some people is in front of my car. And they did not say, yes, you can film me and try to save my life. So yeah, it's a decision from a CPP, it's not a legal issue. Okay, thank you.
The difference with your cars there is that in this setup, in the daycare hospital, we know that everyone there is, well, almost everyone there has kind of a sensitive profile. It's elderly people with probably onsets of dementia, etc. So I think this might be, yeah, and visitors as well. Yes, but.
Yeah. Actually, if you do not keep the image, if you do not keep information about it, you just process the data, you try to avoid to kill them, and you just forget the data. Yeah, you have no data about no one at the end. Yeah. If you process some data and try to recognize voice, do speaker very separation, let's say. Yeah, you will store data. In this case, there is a problem because they do not, they do not consent to do so. But just you took an image and you try to avoid people. Yeah, for me, they're not so.
Yeah, I mean, I guess it's the first time we have such kind of experiments in a hospital, so we are quite happy to be able to conduct them already. That's and maybe next time we will do something, one step ahead, right? So I guess we have to go one step at a time.
Thank you. So maybe either we have one very short question, yes, and that will be the last one.
I would just like to know about the localization of speakers. So I think the question would be for you. Is it purely based on audio signals, or does the camera help you to localize the person, or is it both? Okay.
Yeah, it's
Thank
both.
you. Thank you.
All right. So I have maybe 2 final comments. first one, you heard me stepping in a lot of time on the answers. This is because some of the partners are not here yet, so I am basically stepping in when the partner is not here, which means that what you saw today, once more, is the joint work of a lot of people, right? And you will be able to talk to them during the week. So if you're interested in some of the things, and we told you on Friday or on Thursday, or be sure to reach the person that will give the talk, like one of the two talks, so that they can give you more information. The second thing, we will leave the dialogue demo on during now the reception that will be just here in the hall. We will not leave the navigation demo on for safety reasons. We do not trust ourselves that much. No insurance for that, no. No, I have no insurance for the verbal hallucinations that Ari can have either. The only thing that we would like to ask you is to not come in the room with food or drinks. Okay, so you drink or eat whatever you want here outside, and then if you want to try the dialogue demo, you leave your drink or whatever, and then you come and try to chat with Ari. All right. So thanks a lot for your attention.